We are diving straight into closing the train test gap in world models for gradient-based planning by Parthasarathi et al. From researchers at Columbia and NYU.
And this one is a real game changer. The core idea is that world models are fantastic for planning, but the most efficient way to use them, gradient-based planning or GBP, just underperforms.
Right. It fails compared to sampling methods like CEM, and that's because of a fundamental mismatch between how they're trained and how they're used, the so-called train test gap.
Exactly. So this paper introduces two new fine-tuning methods to fix that. Online world modeling, OWM, and the one that really shines, adversarial world modeling, AWM.
And the headline result.
The headline is that AWM lets gradient-based planning finally match or even beat the big, slow, search-based methods. And here's the kicker. It does this with a tenfold reduction in computation time. This isn't just a small tweak. It's a fundamental shift.
Okay, let's unpack that. For you, our listeners, world models are a critical concept. They're the shift away from classical physics, right? They don't need first principles.
Not at all. They learn the environment's dynamics directly from data. High-dimensional stuff like raw images.
And they're not starting from scratch here, which I found really interesting.
No, and that's smart. They use a frozen Dino V2 encoder. This gives their system a really high-quality visual representation right out of the box. So the model can just focus on one thing, learning the transition dynamics in that latent space.
So once you have that robust model of the world, planning just becomes an optimization problem.
Right. At inference time, you're just solving for the best sequence of actions to get from point A to point B in your latent space. It's so much more sample efficient than, say, traditional RL, where you're doing all this trial and error in the real world.
Okay, but this is where the paper really draws its battle lines, right? The divide between different planning methods. On one side, you have the search-based planners.
Yep, CEM, MPPI, things like that. They're gradient-free, which is nice, but they're basically brute force. They sample thousands of possible action sequences.
And run slow rollouts in the world model for every single one.
Exactly. It's incredibly computationally expensive. It just doesn't scale well, especially when you need to make decisions fast.
And on the other side is the theoretical hero, gradient-based planning, GBP.
Well, it promises so much, right? The world model is differentiable, so you can just use gradient descent to optimize your actions end to end. You just skip all those slow, expensive rollouts.
But in practice, it's been a disappointment.
A huge disappointment, historically. The potential was there, but it would just fail to converge or get stuck. And that failure, that's the train test gap in action.
So this gap, they identified two core reasons for it. The first one is that the planner itself drives the model crazy.
That's a great way to put it. The first hypothesis is what they call out-of-distribution states, or O. Your model is trained on, nice, clean, successful data.
But the optimizer doesn't care about that.
Not at all. Gradient descent starts exploring these weird intermediate actions, things the model has just never seen before.
And because it's never seen them, the model's predictions start to fail.
Precisely. And it's a long chain of predictions. So one small error at the beginning, it just compounds, it spirals, and your whole plan becomes useless.
Okay, so that's the data problem. What's the second hypothesis?
The second one is the difficult optimization landscape. Even if your model is technically accurate, the surface it creates for the optimizer can be a nightmare.
What do you mean by surface?
Imagine you're trying to roll a ball to the bottom of a valley. If it's a smooth bowl, that's easy. But the landscape from a vanilla world model is rugged. It's full of bad local minima, flat regions where gradients disappear.
So the optimizer just gets stuck.
It gets stuck, or the gradients just become useless. So even with a perfect model, if the landscape is badly behaved, GBP will fail.
Which brings us to their first solution, online world modeling, or OWM. And this one is aimed squarely at that OWM problem.
It is. It's a really elegant feedback loop, kind of like what you see in imitation learning.
How does it work?
So you start with your pre-trained world model. You use GBP to plan an action sequence. Now, because the model is still fragile, this sequence is probably a bit weird, a bit OD.
Okay, so you have this imperfect plan.
Right. Then you take that plan and you execute it in the true environment simulator, the ground truth. This gives you what they call a corrected trajectory.
So you see what actually happens when you try to execute those weird actions.
Exactly. And that corrected trajectory now contains valuable information about those OD regions the planner likes to explore.
And the final step is just fine-tune the model on that new data.
That's it. You're constantly updating the world model, teaching it about the very mistakes the planner is likely to make. It's a bit like Dagger, where an expert corrects a policy. Here, the simulator is the expert, and it's teaching the world model how the dynamics really work in those tricky spots.
Okay, that makes perfect sense for the ODE data problem. But OWM needs that true environment simulator, which you might not have, or it might be super slow.
A huge limitation.
So how do you fix that second problem, that rugged landscape, without ground truth? And I think this is where adversarial world modeling, AWM, comes in.
This is the brilliant part. AWM tackles the smoothness issue entirely inside the model itself. It uses adversarial training.
You're attacking your own model to make it stronger.
In a way, yes. The objective is to introduce tiny perturbations to the model's inputs, the latent state and the action. The system actively looks for the worst possible tiny changes.
The ones that make the prediction error skyrocket.
Precisely. It finds the model's most fragile points and then forces the model to become robust to them. And when you do that, you're implicitly smoothing out the gradients.
So if you could see the lost surface, it would look different?
They actually show this in the paper. The original Dino world model has these sharp, narrow ravines around the best solution. After AWM, it's this beautiful, broad, smooth basin. It makes it so much easier for gradient descent to find its way home.
Now, adversarial training sounds computationally expensive, PGD attacks and all that. That would kind of defeat the purpose here, wouldn't it?
It would, and that's why they found a clever shortcut. They approximate the worst-case attack with a single step. It's basically the fast gradient sign method, FGSM.
And that's efficient enough.
It's remarkably efficient. It only takes about twice the backward passes of normal training, so you get all this robustness and landscape smoothing, but without needing expensive rollouts and, crucially, without needing the real environment simulator. That makes it perfect for real-world applications.
Oh, wow.
And the validation really proves it all out. They built their models on that Dino V2 architecture and tested it on 3 main tasks. Push-T, which is block manipulation, point maze, and wall, which are navigation tasks.
And the real test is always the closed-loop MPC setting, right, where you have to replan constantly in real time. How did AWM do there?
The results were decisive. Just massive improvements over the baseline. Open-loop success went up by 18% on Push-T, 30% on wall. But the really big story is how it stacked up against CEM. Wait, hold on. I thought the whole point was you had to trade performance for speed. Are you saying they just got rid of that trade-off?
Pretty much. In the closed-loop setting, GBP with AWM consistently matched or even outperformed the expensive CEM baseline. We're talking 94% success on point maze and wall. It's incredible.
So you get better performance faster.
Exactly. Now, to be fair, just switching to a better optimizer like Atom helped GBP a lot. But Atom alone wasn't enough to beat CEM. The fine-tuning, either OWM or AWM, was the secret sauce.
And they actually proved they closed the train test gap, right? They had a metric for it.
They did. They measured the difference in model error between training and planning. For the baseline model, the error was worse during planning a negative value. That's the gap.
And after their fine-tuning.
And the gap disappeared. Both OWM and AWM reversed the trend. The model became just as robust during planning as it was on its training data. It's no longer surprised by what the optimizer wants to do.
Which brings us back to the practical result for anyone listening, the speed.
The speed is just staggering. GBP with AWM matches, or beats CEM, and yes, over an order of magnitude less time. That 10x reduction is real. For anyone building real-time systems, robots, anything where latency matters, this is huge. GBP is now a truly viable option.
And this wasn't just a one-off for one architecture, right?
Nope. They showed it worked with the Iris architecture, too. It held up on long horizon planning, out to 50 time steps. It's a generally applicable technique.
They also tweaked the loss function itself with something called weighted goal loss.
Right, WGL. A clever idea. Instead of only caring about the final state reaching the goal, you also encourage the intermediate states along the planned path to get closer to the goal.
Like a set of breadcrumbs.
It's a form of soft guidance, yeah. They found it helped, but the weighting matters. For long navigation tasks like point maze, it was best to really emphasize being close to the goal at the very end of the trajectory.
So to wrap this all up, the breakthrough here is crystal clear. The authors took gradient-based planning, which was always this promising but fragile idea, and made it robust.
And they did it with these clever, cheap data synthesis techniques, OWM and especially AWM. They've turned GBP into a high-performing and, crucially, a 10x more efficient alternative to those slow search methods.
The big lesson seems to be that you can't just focus on the planner at test time. You have to fix the world model during training.
That's the core insight. Modifying the training procedure to make the model robust to the kinds of weird states a planner will explore, that's the key. AWM gives you an incredible advantage in efficiency and stability it's going to be hard to ignore going forward.
So what does this all mean for the future? We've seen these adversarial methods make single timescale world models incredibly fast and stable. If you can get this level of performance there, the next logical step is to scale it up. Just think about how these fine-tuning methods could radically impact long-horizon decision-making if you applied them to multi-timescale or hierarchical world models. Achieving stable, efficient planning across huge, abstract time horizons, that's an avenue that's now wide open for exploration.